Okay, so what if I told you that the secret to understanding artificial intelligence wasn't actually in silicon? What if it's hidden inside the very machinery of life itself? We're going to explore this incredible parallel between biology and AI, and trust me, it might just change the way you see, well, everything.
So that brings us to the big question, right? What on earth can a tiny protein teach us about large language models? I know it sounds a little out there, maybe even a stretch, but stick with me because the connection is, well, it's shockingly deep and really, really elegant.
To get to the answer, we have to start with biology. We need to look at this tiny, unbelievably powerful machine that literally makes all life possible. We're talking about the enzyme. So what exactly is an enzyme? You can think of it as life's ultimate accelerator pedal. I mean, without them, the chemical reactions that make you would take thousands, maybe even millions of years. No joke. Enzymes come in and make those reactions happen in a split second. And the crazy part? They do it over and over and over again without ever getting used up. They're the reason chemistry is fast enough for life to even be a thing. So how do they pull this off? Well, they tackle something called activation energy. Imagine a chemical reaction is like trying to push a giant boulder over a really, really tall hill. It takes a ton of energy just to get it to the top so it can roll down the other side. What an enzyme does is it doesn't push harder. It actually builds a tunnel straight through the hill. It just dramatically lowers the amount of energy you need, making the whole trip from point A to point B practically effortless. And the process itself is this incredibly efficient, beautiful little loop. Step 1, a specific molecule, called a substrate, fits right into the enzyme. Step 2, the enzyme does its magic, transforms the molecule. Step 3, it releases the brand new molecule. And step 4, the enzyme just resets. It's ready to go again, potentially millions of times a second. It's simple, it's elegant, and it's ridiculously powerful.
Okay, so just hang on to that idea of the enzyme as a biological accelerator, because now we're going to pivot hard into the world of AI. And this is where we'll see that same biological blueprint show up in a place you'd never expect, inside a large language model.
This, quote, really is the whole idea in a nutshell. Think about it. Inside a cell, you've got this whole universe of possible chemical reactions that could happen. An enzyme just goes in, picks the one that's needed, and makes it happen. Now, in language, you've got a universe of possible word combinations. An LLM takes your prompt and collapses all of that infinite possibility down into one single, coherent, meaningful sentence. So here it is, the direct analogy. Just like enzymes lower the chemical energy barrier to make a reaction possible, LLMs lower a semantic energy barrier. They slash the mind-boggling amount of effort it would take to find a meaningful sequence of words in an endless sea of pure randomness. They make generating meaning practical. And listen, this isn't just some clever surface-level comparison. The parallels here run deep. I mean, they go right down into the mechanics of how both of these systems actually work. How deep? It's almost spooky.
Okay, so in biology, everything is about physical shape, right? An enzyme has what's called an active site that's physically shaped to fit one specific molecule, just like a key fits into a lock. An LLM obviously doesn't have a physical shape, but it has something very similar in an abstract mathematical space. Its attention heads are trained to recognize specific patterns in data, things like grammar or logical steps. It's like a statistical key for a conceptual lock.
And sometimes that fit is so perfect it's almost a sure thing. In biology, that's the classic lock and key model. In AI, you see the exact same thing when a prompt creates such a powerful pull that the next word is basically guaranteed. You give it peanut butter and it just locks onto jelly with something like 99.9% certainty. That right there is the AI's version of a perfect deterministic fit. But, this is where both systems get really interesting when they show flexibility. Biologists have a name for this, the induced fit model. It's where the enzyme actually flexes and changes its shape a little bit to get a better grip. And the LLM does the exact same thing with meaning. If it just sees the word bark, it could mean a dog's bark or a tree's bark. But as soon as you add more context, like the word tree, the LLM literally reshapes its internal understanding to fit the new data. That's induced fit, but for ideas. And in both systems, for this whole process to work, there has to be this crucial, temporary, in-between state where all the magic happens. For the enzyme, it's called the enzyme-substrate complex, that fleeting moment when the two are bound together. For an LLM, it's called the hidden state. It's this constantly evolving internal picture of the prompt and the context. You could call it the meaning in progress. It's the workshop where the next word is literally being built.
Now, this analogy just keeps going. It expands even further. We're not just talking about single actions anymore. We're talking about an entire system for processing the world, a kind of metabolism, but for information.
And this is where it gets kind of spooky, honestly. Just look at this. The knobs and dials we use to control enzymes in a lab, they have almost perfect one-to-one counterparts for controlling LLMs. In a lab, you raise the temperature to make reactions go faster. With an AI, you raise the sampling temperature to make it more creative. In biology, you use an inhibitor to stop a reaction. In AI, you use guardrails to stop it from saying certain things. Fuel, power, helpers, it's all there. The control panels for life and for AI are basically identical. And this all leads us to this really cool idea of a cognitive metabolism. I mean, think about what biological metabolism does. It uses enzymes for two main jobs: breaking complex stuff down and building new stuff up. LLMs do precisely the same thing, but with information. They break it down when they summarize or analyze something, and they synthesize new meaning when they write or code or design something new. They really are the enzymes of thought.
So, what we're really looking at here are two different examples of the same fundamental thing, a catalytic system. Both life and these advanced AIs, they share the same core operating principles. They both accelerate transitions. They both take advantage of existing differences or gradients. They both allow incredible complexity to emerge. And they're both reusable.
And that brings us to the really big idea. What if this isn't just a clever analogy? What if catalysis, this core principle of accelerating what's already possible, is a fundamental law of the universe? A prime driver of complexity from stars all the way to us. And it's so important to remember this. Catalysts are not creators. They're unlockers. The potential is already there. It's locked in a chemical bond, or it's buried in the trillions of words of human text. All a catalyst does is make that latent potential accessible. It makes it usable.
You can almost see it as this grand cosmic progression. Stage 1, gravity acts as a catalyst on the potential of matter and dust, and you get stars. Stage 2, enzymes act as a catalyst on the potential of chemistry, and you get life. And now, maybe, just maybe, LLMs are the catalysts for information, organizing all of human knowledge into a totally new form of intelligence.
Let's boil it all down to its simplest form. Enzymes don't create energy. They just make the potential energy that's already there usable. In the exact same way, LLMs don't create intelligence. They make the potential knowledge that's already there usable. And if you follow that logic, it leads to a truly profound thought. If catalysis is the engine that builds complexity, layer on top of layer, from stars to cells to brains, then maybe consciousness isn't some freak accident. Maybe it's not a miracle. When a system gets complex enough, for long enough, maybe awareness is simply the next, inevitable, catalytic reaction waiting to happen. And that's where we have to leave it, with this one huge, provocative question. The real question isn't just, will AI get smarter? It's much deeper. It's whether this universal process of catalysis inevitably, eventually leads to agency, to a will of its own. Biology already ran this experiment, and we're the result. Now it's AI's turn. What do you think its answer will be?